All right, so because there is a very much a connection between derivatives and integrals, a lot of what we did with derivatives, we're also going to do with integrals. And you'll remember that with derivatives, we always wanted x to a number in the numerator. So the same goal is going to happen here with integrals. Our goal is going to be to get x to a number in the numerator. And you'll also remember kind of our common tricks that we had for getting that x to a number in the numerator was to rewrite radicals and exponents as appropriate, basically to get them into the numerator. And then one common thing that we had was that if there was one term in the denominator, then we would split that up. So for example, you might remember like if it was like x plus 1 over x squared, before we had the quotient rule, what we would do is we would split that into x over x squared plus 1 over x squared, and then simplify from there, and then take the derivative. So that's going to be what we're going to do here with integrals too, is we're going to, if there's one term in the denominator, split it up, and then integrate both of those terms or how many ever terms we have. And then our last one, of course, our common simplification step was to distribute or FOIL as necessary. Now, keep in mind that you are going to lose the integral sign as soon as you do this add 1, divide by the new exponent, and you add the plus c to represent that arbitrary number. But basically, we're trying to use this power rule as much as possible. And the way we use that power rule is to get x to a number in the numerator. So if you're looking at this x to the ninth, that's ready to go. It has that x to a number in the numerator, so we will simply add 1 to the exponent and then divide by the new exponent. And then of course add the plus c.